Welcome everybody to this WRRC Hawai seminar in a different building today, post building, freshly painted. Hope you like it. Thanks for all making the journey here. Today it's my great pleasure to introduce Dr. Larry Barber, who is a research geologist with the U.S. Geological Survey in Boulder, Colorado. He graduated with a MSc and a PhD from the University of Colorado Department of Geological Science. And his area of expertise is analyzing emerging contaminants by gas chromatography, tandem with spectrometry. Okay, those are words they're not in my Dutch vocabulary. So his research focuses on the interactions between chemistry, hydrology, and biology to establish a holistic understanding of contaminant behavior and impacts. And today he will talk on natural and contaminant chemistry of freshwater streams, groundwater, and wastewater treatment plant effluents on the Hawaiian Islands. So please join me in welcoming our speaker.
Well, I got to say, it's a great pleasure to be here today. I love coming to Hawaii. It's a beautiful place. And it's not just a beautiful place to visit. I find it's a beautiful place to work because there's a lot of critical water resource issues, and being a scientist, I can never sort of take my mind away from the research I do. And I found over the years that it's really amazing to be able to come and work in places, and you learn a lot about the people, about the culture, about the issues. So I've given a few talks out here over the years, but this is the first time I've actually been able to focus on the research that we've done. And this is a bit of a cumbersome sort of title about, organic, blah, blah, blah. But really it's about how do we better understand our water resources and the way that they interact with the environment around them. Figure out this technology. Like with all science today, it really does take teams of teams to carry out some of the investigations that we do. That the issues are so big and broad, you can't really answer them with a single focus. So this is just a list of a few of the collaborators. It includes my USGS colleagues, including Steve Anthony, who's here with me today, my academic colleagues from St. Cloud State University, and then interacting with a number of government and NGOs here on the islands. And so people like Chuck Glay and Carl Berg, kind of help with when you go to a place and you need to meet the local people. Well, you need to have a local contact to be able to get access to things like sampling sites and local kind of information. At the USGS, one of the things that we tend to specialize in is this integrative water research. And so really trying to look at the big picture. This always involves a collaborative set of partnerships. It involves interdisciplinary science, and now I think we've gone beyond even interdisciplinary to the realm of transdisciplinary. So when I talk about transdisciplinary, what does that mean? And it really is multidisciplinary work with people that historically would not have worked together. So a geologist and a molecular biologist a decade ago would have never been able to interact very effectively. And part of what I consider to be transdisciplinary research is when you have to learn another language. And what I mean by that is if you're going to be talking to an endocrinologist, you need to understand the jargon and the terminology. So science is kind of like a foreign language, and that to me is when you have to actually learn things that you're not familiar with, then you're probably doing the right thing of pushing the edge of science. My degrees and my training is in geology, so I always start from this geologic perspective, but really we like to take the geology to understand the hydrology and then use the chemistry to better understand those two, and then using all three of these to interface with the biology and the ecological component of the environmental systems that we're working with. And it begins with understanding landscape processes. How does water move? What does it move across? Then as the interactions with the environment occur, how does that impact human and aquatic health, wildlife health? And then ultimately the idea is to take all of this information and feed it over into the resource management domain so that policy making can be done based on solid scientific evidence. And that is often a bit difficult, so you have to have a really good story here to be able to have any impact on water resource management. Part of this integrated approach is using these watershed type of investigations, and these are some of the scaling issues that we have to work with. So for instance, we did a lot of work on the Mississippi River, the largest river in North America, and it really helps us integrate the mainland United States as sort of a watershed instead of 32 states and 1.2 million square miles of landscape. But that's sort of on the outer end on one side of how do you address things that are that big. We've also focused on smaller systems of watershed approaches, such as the mountain to plains approach that we used in Boulder Creek, Colorado. This works nicely when you have systems that are not too big. We find this is a happy spot, about 30 or 40 miles of river, maybe 500 square miles of landscape. Then we can start getting into some of the focus kind of investigations that we need to do. One of the interesting parts of the islands is how we have this mountain to reef sort of approach. And if we look at island of Hawai, for instance, it's not that different than Boulder Creek, except instead of a linear system, we have to look at it's about the same diameter as our linear system. And so instead of having a river that runs for 21 miles or 31 miles, we have a lot of streams that are much more compressed in their dimensions. This also fits into the kind of approach of everything that happens within the watershed, both naturally and human induced, is reflected in the water. One of my earlier colleagues, the guy was, he defined himself as a potamologist. Anyone know what that is? That's a water scientist, you know. So if you think about like a hippopotamus, it's a potamus, and so he always kind of like this, well, I'm a potamologist, and I'll not go down that long story. Part of the question that we really want to ask, though, is what is in the water? And when I do that, I like to really ask that question. What's in the water? You know, what is the composition? It's H2O, we know that, but then it has a lot of other things in it. And I've been focusing over the last couple of decades on what we call contaminants of emerging concern. And these include synthetic and natural chemicals, basically anything on the periodic table. Obviously, a lot of the work is done over here in the carbon, oxygen, nitrogen, phosphorus realm. That's sort of the biological activity. But there's a lot of the periodic table that get into the realm of what we call, say, organometallics. So you might be finding that, say, zircon and carbon form some sort of special molecule that has a particularly important function in technology. But when we have these terms like contaminants of concern, then we immediately go into CECs. And if you're talking to people that are not really into CECs, you've lost them because they go, what on earth is a CEC? And so it's really an umbrella term that doesn't have a definition. It's whatever you want it to be. It can include pharmaceuticals, hormones, surfactants. Microplastics fit into the CEC, insecticides, disinfectants, fragrances. The list can go on and on. And this will be sort of a theme that I'll be touching on today, is every term that we use has almost an infinite breadth that you have to address. So when you hear someone saying a CEC, you know, you really should be asking the question, what do you mean by that? Let's be more specific. What compound? What are the constituents that we're really concerned on? And as an example of modern CECs, we can look at PFASs or PFAS, and these are called per and polyfluoroalkyl substances. Has anyone here heard about PFASs? Okay, yeah, again, they're getting a lot of attention. The only thing I hear as much as PFAS is microplastics. But the PFAS, it really is becoming an emergent concern. It's a contaminant, of course, it's human-made, it's not in the environment naturally, but it's of emergent concern because in 2016, the US EPA came up with a health advisory level which says that waters that have greater than 70 parts per trillion of the PFOS and PFOA potentially present a human health risk from the drinking water perspective. Again, you can see now we've got CECs, PFAS, PFOS, PFAA. With my southern accent, you know, people can't determine whether I'm saying PFAS or PFOS. You know, again, an A or an O means a whole lot of things. PFAS is a very general, broad class of about 3,000 compounds. PFOS, perfluorooctyl sulfonate, is a specific molecular compound that we can put our fingers on. So, you know, abbreviations are really confounding this typical issue, but it's a whole lot easier to say PFAS rather than per and polyfluoroalkyl substances time and time again. Whoops, excuse me. When we think about the USGS, it's a nationally distributed organization. We have science centers and offices in every country, in every state within the country. Often states have multiple districts. Hawaii has one, California, Colorado. And so we really have to be thinking of national scale kind of issues to get away from sort of the localized perspective and see how does it look in the context. So these are just two of the papers that have come out not too long in the distant past. Bradley et al. 2017, we looked across the country at about 38 streams in 30 states. We measured a lot of CECs, we detected a lot of them, and the concentrations were down in this part per trillion level from 1 to 10,000 parts per trillion or nanograms per liter. What this study and some of our previous work have really shown, though, that's what's unique about a lot of these CECs that we're working with is that they're what we call bioactive by design. So if you take something like calcium, that's natural. If you take something like a chemotherapy agent, that is a molecule that is designed to have extreme and exquisite biological function. So suddenly, these concentrations of 1 part per trillion mean something. Historically, you know, people would say, oh, you analytical chemists, you're just always wanting to measure lower and lower levels. But in fact, we need to be able to measure these really low levels because that's where the effects occur. So it's not just a trivial activity. Here's another study that we just published, but this is kind of looking, it was a national survey. We looked at 21 sites in 17 states, but instead of surface water streams, we were looking at stormwater runoff. And what we found is we measured a lot of the same CECs, we detected a lot, but as not surprisingly, a surface water event, or runoff event, is going to have higher concentrations than sort of the average. So the idea is that much of what is making it into these stream sites is coming from surface water runoff, in addition to a lot of other different types of sources. So when we think about one of the main sources of those chemicals to the environment, particularly the biologically active pharmaceuticals, things like that, wastewater is one of the predominant sources. And I no longer refer to phenomena as wastewater disposal. They're not sewage treatment plants, they're water reclamation facilities, because that sewage and that wastewater is in fact a very valuable water resource, particularly as we become more and more stressed with our changing in climates and population and so forth. So when we think about this water reclamation reuse, it becomes a rural resource management issue. It can be used for the potable supply. So there are places in the country that have direct toilet to tap sort of approaches that the wastewater gets put right into the water distribution system. That's what you have to do when you don't have any fresh water available. You got to use the water you have. There's what we call this indirect reuse, which is wastewater gets disposed of, but it doesn't go away. So it becomes a significant component of surface water and groundwater systems. So here's just a picture of the United States. Each of these dots is showing sort of a wastewater stream type of system. And anything that's in red, that means it's greater than 15% wastewater all the time. Out in the western US, many of our streams are, for instance, what they call 99-99. 99% of the time, 99% of the flow is wastewater. There is no fresh water coming into the system. Streams would not have water in them if it were not for the wastewater discharges. So this has a lot of implications for that resource management perspective, because source water characteristics differ. Different sources have different water. The level of treatment that water goes through influences the potential impact. We think a lot about this conjunctive reuse. How do you get the maximum benefit from the resources that you actually have available? And if this maximum benefit can be perceived in things like ecosystem health through in-stream flow. So, you know, a lot of streams out west that people complain, it's like, well, there's wastewater in the stream, but our answer is there would be no water in that stream, therefore there would be no habitat, there would be no aquatic organisms. And then obviously human health is always an important issue that we have to think about because we're one of the primary users of good water. The Hawaiian Islands and island systems in general, I find very fascinating because they're a glimpse into the sustainability of freshwater ecosystems. That there's no water really coming in a river. It's coming from the river in the sky, but basically these are isolated systems. It's got a very compressed hydrologic cycle compared to 1,500 kilometers or miles. You have a 2-mile river. Land use practices become very important. Water reclamation and reuse never goes away. And on island systems, it's really important to protect these sole source type of aquifer recharge zones. There's a lot of potential anthropogenic impacts that come along with this. There's atmospheric deposition. Dust and gases get transported globally and deposited on the islands. Urbanization can be a significant component of anthropogenic contributions. The Honolulu complex is a very good example. Tremendous amount of chemistry used in that basin. Wastewater also comes with the biosolids where you're treating the water. You also have to deal with the solids that are associated with that. These are often linked to the agriculture. Biosolids can be applied as manure management or as a fertilizing components. Transportation doesn't get a lot of attention, but it's really important for emerging contaminants because when you think about a vehicle, that's a whole lot of things. There's hydraulic fluids, there's rubber in the tires, there's emissions from the tailpipe. So transportation is a major source of these chemical inputs. Energy production is a big one. And then tourism and recreation helps focus a lot of additional inputs onto these very narrow, restricted environments. To illustrate sort of the sustainability issue, this is a paper that was published in 2013 with out here in the islands, and Delwyn Oki, who is one of my colleagues. It was the study of stream flow from 1913 to 2009. And the take-home message from this slide is on every one of these long-term trend stations, we have this declining slope, meaning that the and the axis, I apologize, there's so much information, but this is base flow in percentage of the mean flow. So that drop is relative to the mean, but you can see a consistent diminishment in the stream flow on the islands over time. And this really feeds into the water reclamation and reuse. As that stream flow goes down, at what point do you need to start taking more advantage of the other water resources you have? And that's where the reuse becomes an important component. This is sort of showing the amount of wastewater treated on the islands, and it hasn't changed that much over the year. What we see is a very big increase in water reclamation and reuse that then sort of flattened off and began to drop. And this water reuse is used primarily for irrigation of golf courses, industrial applications, cooling waters, agriculture, and landscaping, and then some other components. But the importance of reuse in terms of a resource is becoming more pronounced. Now, when you go, well, so what in the reuse? Here's just an example of some work done on Hawaii where we were looking at the effect of some of the chemistry in the wastewater treatment plant effluents and how they affect the transport of cryptosporidium. And what we can find is that if you apply effluent to these soil columns, that it modifies the colloid characteristics and the soil characteristics and facilitates transport. So over here we have a control, say for instance, looking at cryptosporidium. The control has, and this is partitioning into the organic phase. So you have a lot of absorption of the cryptosporidium to the soil, therefore it doesn't get transported into the groundwater drinking water supply. But in the presence of what we have here, Swanee River humic acid, which is a natural organic matter, or SDBS, sodium dodecylbenzene sulfonate, which is a surfactant. That's what's primarily the main ingredient of like shampoo and other components, that it really makes that cryptosporidium, which is basically immobile in the soil, and it makes it just zip right through because it modifies both the soil characteristics as well as the surface chemistry of the micro particles. So wastewater actually does have some implications, and these are all secondary. It has nothing to do with the chemistry you're going to be exposed to. It really has to do with how that wastewater modifies other components. So to get into the current study that I'm going to be talking about is starting in roughly 2013, we initiated a series of small investigations which today are going to be presented as kind of an aggregate study. And that's what we've had to do because we really, haven't had a core line of funding to do the big massive study, but we know the issues are out there and we have to get data to inform future activities. We looked at Hawaii, Oahu, Maui, and Hawaii. We sampled some of the canals and ditches. We sampled fish, I'll get to later, ocean precipitation, spring surface water, tap water, wells, and wastewaters. Overall, we collected about 90 samples, but a lot of them, say, fall over here on the Kona coast of the Big Island, which was a targeted focus study. We got quite a few sites here on Kauai because of the abundance of surface water systems. So overall, I think we sampled about 90 to 95 different locations. Some of them we did pretty comprehensive work. Some of them we just did a quick grab to sort of look and see what we could come up with. Now this is where the gas chromatography tandem mass spectrometry. Now you can give me some geophysical tools that I can't pronounce too, like well, I wouldn't be able to pronounce it if you gave them to me. But the GCMS and our other analytics is we collect the samples, we do the studies, and then we subject them to what we consider a hierarchical chemical analysis approach. And we try to measure as much in the water as we possibly can, and we start with measuring very simple parameters like pH, DO, conductivity, and that doesn't cost very much, the price of the instruments. We also look at bulk things like the nutrients, carbon, nitrogen, phosphorus, major ions. The cost goes enzyme-linked immunoassay is another tool we have, that this has sort of an intermittent cost. Then we can apply tools like isotopes and the trace elements, which increase in cost. And then when we get into sort of the CECs, contaminants of emerging concern that are of most interest right now, one of the real challenges is the cost of those analyses is very high. I mean, we're talking in between $300 to $600 per sample. And at that point, once you start doing a lot of water quality sampling, your budget needs to be really large. That's why we use this hierarchical approach. We can measure everything using these tools, and we can learn a lot, but it won't necessarily tell us about these specific compounds that we may have the greatest interest. But I always try to avoid is spending all my time and resources and not seeing anything, and then saying, well, this was a great study, we spent $200,000, and we didn't see anything anywhere, and I can't tell you more than that. Well, we will always see nutrients, major ions, and isotopes, so we never come away from studies empty-handed. Well, this all has to be put into this hydrological framework, and the hydrological framework has to be defined by the geology, the physiography, the meteorology, and the hydrology. So when we even think about a framework, it gets pretty complicated in what underlies that. So basically, this is Oahu, and depending on where you are on the island, water is going to be flowing in different directions, both at the surface and groundwater. At the surface water, we get runoff to the coastal environment. The groundwater can recharge right at the interface, or the groundwater can be deposited, transported, and discharged further offshore. But bottom line, anything that happens here on the landscape is going to end up here in the coastal environment. And the Hawaiian Islands have an island shadow that extends off into the North Pacific. So even though it takes subtle measurements, you can see the impact of these islands and these coastal zone discharges at quite some distance. So now we are thinking about the hydrological context. We measured hundreds of constituents, and you go, what do you do with that? And I always develop a severe case of mental fatigue when I start taking 90 samples and 500 constituents and 10 sampling points. My brain simply gets overloaded. So that's where we have to use things like these multivariate statistical techniques such as principal component analysis, hierarchical clustering, and some other tools that we have, which really help us kind of look at the large aggregated data set. It lets us tweak out what are the key relationships. And so if we just take the PCA, principal component analysis of the source water characteristics, what we can find is about 50% or more of the variability can be related by two factors, one being the range and composition from precipitation to seawater, and then the other one is the range and composition from sort of landscape springs up to wastewater discharges. Now we can put it into a few other statistical filters, and then that will start saying, well, how do you define, say, this landscape impact on the surface waters? And that is based on this chemistry. So we use these tools to figure out which chemicals are the ones that are going to tell us the most, and not focus on the ones that maybe tell us the least in terms of determining source characteristics. So we're able to come up with a number of tracers of different source waters. For instance, seawater is enriched in boron, lots of other things, molybdenum, strontium, uranium. The landscape sort of sampling is dominated by things like the rare earth elements, cesium, cerium, europium, lanthanum, yttrium. The list goes on. These are trace elements that often don't get applied to hydrologic investigations. They've historically been applied to geologic investigations. And then the wastewaters have some very unique chemicals that I call anthropogenic chemicals. They're things that we use and enrich them in our wastewater. They include bismuth, cobalt, gadolinium, obviously phosphorus, antimony, zinc, copper, other things fall into that. So by using these sort of tools, we're able to come up with some indicators that tell us something about source water characterizations. And we can take that data and from these large data sets of inorganic chemicals, organic chemicals, lots of locations, sampling points, and determine which kind of source water there is. And because we have so much data, I don't want to go into this too much, but we can take, for instance, lanthanum is a landscape indicator. These are shown by, pardon me, here's some data from Kauai, Oahu, Maui. We don't have as many sites, and then the Big Island. Well, the lanthanum tells us about the landscape, where the antimony tells us more about the wastewater. So we can start saying, well, when you have this increased antimony, that's really a strong wastewater signal. And on the mainland, in most of the places that I work, boron is a really good indicator for wastewater, but that doesn't work out here on the islands because of the marine influence, that you start getting boron coming from sources other than wastewater treatment plants. So to focus down a little bit more on some of the data, these are results from a study of wastewater reuse on the north central Oahu aquifer. And this was kind of a unique situation because basically the question was, does wastewater reuse have the potential to impact deep groundwater aquifer systems? And there aren't that many places on the island where wastewater is discharged to a surface body and then reused. It's typically wastewater might be directly used to irrigate a field, but this is a case where a wastewater treatment effluent has been discharging into a reservoir for many decades now. It was recently upgraded from R2 and R3 to R1 in 2014. This reservoir is fed by stream water, so once the wastewater treatment plant discharges, I think right through here, it then mixes with all the water in the reservoir, and then it's passed out of that reservoir through a ditch where it's applied to agricultural lands and other areas. And this would be what we call that de facto reuse, that if the wastewater is discharged into the reservoir then mixes it all up, it comes out, and then we're reusing it. So the question is, how much wastewater would be in these reservoir and irrigation ditches versus what would be in the effluent itself? And these are just some of the data. So on this axis, on the x-axis here, we have the wastewater treatment plant, that ditch. It's actually more like the reservoir water. So this is not ditch such as agricultural runoff. This is a discharge point from the reservoir. We have, three groundwater wells. These are public water supply wells. These we call the inland or the high level wells. They're up near the reservoir. And then we have two other deep groundwater wells which are near the coastal environment. And if we take something like nitrate, which is a pretty standard measurement, that says, oh yeah, well you can distinguish the wastewater from the ditch, and these high-level wells have lower nitrate than the coastal wells. But we can take that a step further using isotopes and say the del N15 of the nitrate And you can start clustering those samples in a maybe a little bit more definitive way, but it looks pretty much like the same, that our surface waters plot differently than the high level than the coastal. We can apply that to elements like boron. Now, one thing that happens here is we start going from things that are in the part per million level, the milligram per liter concentrations of nitrate, to once we get into boron, we're down in the part per billion level, the microgram per liter concentration. And we see a similar set of relationships. And when we look at the boron isotopes, we can see that the patterns has sort of changed around, but we can distinguish surface waters from coastal, from high level waters. And the approach that we like to take are multiple lines of evidence. So when you have a concentration and an isotopic, when you have two concentrations and two isotopics, that begins to tell a pretty definitive story that isn't just hanging on one piece of information. We can also use other tools such as trace element ratios. And here's a case, now again, we're down at the part per billion level, the subpart per billion level, that arsenic is, the concentrations here are very low. That's 100 parts per trillion, 500 parts per trillion. But one of the distinctions here is that arsenic is very common in the marine environment. It's a marine constituent, whereas antimony, which behaves a lot like arsenic, they're in the same periodic group, but antimony has a very distinct human anthropogenic input that causes it to be enriched in the wastewater treatment effluent. So we can see that same thing here, that if you're not sampling nitrate isotopes and you do trace elements, you can still use these tools to kind of determine the nature of the source waters that you're dealing with. And then here's one of my favorite constituents, which is a very, very definitive tool. This is a bit of a busy slide, but among the rare earth elements, which is this little box here in the periodic table. Anyone here familiar with rare earth elements? Okay, well, you're all using them every day because every computer, every smartphone, every projector, our entire technology, and a lot of our global geopolitics is driven by rare earth elements because they're so important in technology. And yet they get bumped as this box here on the periodic table. Now, if you look at things like lithium or say carbon, carbon is carbon. Over here you have one box, but that's 14 elements that fit into that one box. The thing that makes the rare earth elements unique is they all have the same charge, plus 3 valence. They all have similar ionic radii, and therefore they all have very similar geochemical behavior. So what we have to do with this rare earth element, the first thing we do is we have to normalize the concentrations to what we call the North American shell composite, or a geologic source, because based on sort of the evolution of the solar system, it's called the Otto Harding effect, which is basically there's more even atomic number elements than odd atomic, more abundance. So if you don't do this normalization, you get a real sawtooth pattern that the even atomic number REEs have high abundance and the low odd have low abundance. So it's really hard to tell, is that high abundance real or different than that low abundance? So we have to do this normalization. And once we do that, you should be generating a line that's fairly flat, where these are the 14 REEs listed from lowest to highest atomic number. And the thing that we describe here is this anthropogenic gadolinium anomaly that's really related to wastewater. And so you can see here that there's this very strong peak here that's wastewater related. And the source of that is medical diagnostics, that a organically complex gadolinium is used as a contrast agent for magnetic resonance imaging. So basically, signals like that anomaly result from roughly 1 person per 100,000 population having an MRI per day. So it really is extremely sensitive, extremely specific, and it only has one use. Now, what's interesting though, when we look at the rare earth elements, you also see things that are related to the natural geologic environment. And so, for instance, islands like Hawaii that are basaltic have what we call this middle rare earth enrichment, and you in fact have a europium anomaly, but you can see that that's one element offset from the gadolinium anomaly. And this feature is really just due to the geology. That's the water falling on the basalt and liberating the chemistry that's associated with that rock type. Most of these are other, and one other thing is you can see that none of these surface water samples, except for this reservoir or ditch sample, have a gadolinium anomaly. So here's a case that wastewater treatment plant has this signal, and that ditch has a gadolinium anomaly that's persisting after all of the mixing and resonance time in the reservoir. So it really is saying that there's about, I haven't actually done the calculations, but I would say from that, maybe about 3 to 5% of the water in that ditch coming out of the reservoir was actually contributed from that wastewater treatment plant effluent. So it's really a very powerful tool. It also lets us distinguish, say, groundwater, which you see has a enrichment in the heavy rare earth elements. Now that enrichment really comes from geochemical processes, and that's another important aspect of these elements. At the kind of expense of becoming repetitious this is the confirmatory aspect of multiple lines of evidence. We can take pharmaceuticals and look at that same wastewater treatment and ditch reservoir system, and we can see that the ditch concentrations are attenuated, but almost all of the pharmaceuticals that we see in that effluent we're also seeing in that ditch water. Therefore, when that ditch water is used for some other purpose, it does carry along with it those pharmaceuticals. And so what are all these? Like, for instance, metformin is it's a anti-diabetic component. What we're seeing are a number of opioids, these things that often end in the "-ol", or opioid or some sort of derivatives. Sulfamethoxazole, antibiotic. Carbamazepine, a anticonvulsant sort of component. So these are the kind of tracers, particularly say sulfamethoxazole and carbamazepine, that we can start using of saying, well, is there any evidence of wastewater in this groundwater supply or this discharge point? And it's pretty definitive. We can keep going further and further down this rabbit hole of tracers and look at things like wastewater components. Here we have HACB. This is an abbreviation of a compound called galactolide, which is a fragrance that's in basically everything we use. It's in our soaps, our shampoos, our perfume, deodorant, etc. It's very biologically active in the sense that you can smell it at extremely low levels. And so again, when you see HACB or galactolide in the water, that means that water has wastewater in it, and you can go from there. So some of the organic tracers that we're most concerned of are the steroids and the hormones, and that's because they're so biologically active, and we actually can do something with them because we know quite a bit. Well, there are a lot of different, these are all natural biomolecules. So 17-beta estradiol is the primary female sex hormone, but it also can oxidize to form estrone or estriol. If we look at the concentrations across the islands, we see that these values range from around 0.1 to 20 nanograms per liter, or parts per trillion. There are a lot of other components in here that we measured, but I don't want to go into now for the lack of time, and I'll be focusing on these estrogenic compounds because they relate to something called endocrine disruption. And endocrine disruption is sort of a global issue, and that human and wildlife really require a normal endocrine system development to be healthy and successful. So the endocrine system begins with your neurological function, your metabolic function, and more importantly, your reproductive function. And so we have to think about the chemical exposures of these very powerful chemicals, the biological modes of action, and adverse outcome pathways. What we mean here by the biological mode of action is you actually understand how that chemical interacts with an organism. So you understand that biology. And then we think about, out of this whole list of all these different compounds we're looking at, the ones that we need to focus on, maybe the first, have this adverse outcome. If you know how a chemical interacts with an organism, human or wildlife, and it has an adverse effect on that organism, those are the areas that we can focus our time and resources on. Here's a really good example of how potent these chemicals are. It's 17-alpha ethanyl estradiol. It looks like the one I showed earlier, 17-beta. The only difference is there's this one little functional group over there. By adding an ethanol in that 17 position, then that's what's become the predominant synthetic oral contraceptive. And when I talk about biological potency, this one molecule, 120 kilograms, roughly the mass of what I used to weigh 10 years ago, I'm a little bit heavier now, I'm probably more like 140, but anyway, that tiny amount, it would just be a pile that's not much bigger than this, is so potent that it can shut down the reproduction of 12 million women on an annual basis. Now that's different than, say, things like petroleum hydrocarbons that may cause a 1 in a million increase in cancer 25 years ago. These are designed to shut down reproduction. So if you're able to shut down the reproduction in a human, what would you think that molecule would do to other invertebrates? It's a contraceptive for fish and mammals and birds and rodents. So when we think about these kind of things, this potential effect on aquatic organisms and health, we're thinking about these endocrine disrupting chemicals, and so we kind of have this complex chemistry, which also means there are complex modes of action, that every molecule can interact with the organism with different modes of action. In this case, it's the estrogen receptor that's very well defined, and we have a target, which is if it's impairing reproductive outcomes, then that is an adverse outcome pathway. So what we have to do is look at this water chemistry. It's very complicated. Lots of compounds can interact with that estrogen receptor. It's always a mixture, so we have to think about mixture effects. Are these compounds additive? Are they synergetic? Are they antagonistic? You have to get a handle on that. And then you have to think about how do that complex chemistry and the mixture effects relate to biology. And that's where we use this relative 17-beta estradiol potency, which lets us determine how potent a particular molecule is relative to estrogen. And then we can add them all up and get what we call the estrogen equivalency quotient. And if we look at the data that we collected on the islands, the EEQ ranges from about 0.1 to 20 nanograms per liter. Again, really low levels, part per trillion. Who cares? Well, because if you have an EEQ less than 1 nanogram per liter, you could kind of go, well, who cares? Because all the evidence says that's below an effect value. But if you have a value greater than 10, you could potentially be shutting down the entire reproduction of, say, an aquatic ecosystem. So when we have an EEQ of greater than 10, that really means that that water has a high risk for the organisms, humans and wildlife, that are consuming it. And one way to get a handle on, well, now we've predicted some risk. We predicted that there's enough estrogenic compounds out there that may be impacting organisms. Part of our study is we looked at endocrine disruption in wild fish. We chose Gambusia affinis, which is mosquito fish. It was introduced back in the 40s or 50s for vector control mosquito. It's called a mosquito fish for a reason. It loves to eat mosquito larvae. That's primarily what it graces on. But we have to look at what is the sex of the organism. And then it has this secondary sex characteristic called the gonopodium. And basically this is a male Gambusia with a fully developed gonopodium. And basically, if we look at these pictures, under normal conditions, the gonopodium is much longer than the other anal fin rays, which are down here. And they have these extended hooks and serrations on them, which basically, as that male fish gets close to a female fish, the gonopodium attaches, it reaches out and grabs her, so to speak. But it's these hooks and components that keep that connection, the hookup, so to speak, going on. Once they're exposed to these endocrine disrupting chemicals, what we find is that the gonopodia is quite shortened, and those hooks and serrae are diminished, which would then mean that this fish here is going to have a very low probability of reproductive success. If we look at some of the data, here's kind of what we would expect, that typically the male gonopodia is quite longer than the female, and we can see that in a number of our sites. But more importantly, this was a sort of an unknown and sort of surprising finding, is that many of the and these are sort of statistically numbers of, from 50 to 100 type of organisms, and we were quite surprised to see that many of the waters, independent of the islands, that the male and females could not be distinguished on that secondary sexual characteristic, which is normally something you can always tell the males from the females. So something is going on, and we don't know what it is. We don't know if that's due to exposure to chemistry, or if it's just sort of, no one's ever looked at this relationship on tropical islands, and this could be sort of the normal, and in fact, this might be the abnormal. We simply don't know. That's why we call this reconnaissance. You got to go out and start looking for things. But what this did with that gonopodia is it actually gave us a biomarker so that we could start looking for an effect. If you can't measure the effect, you can't attribute any sort of environmental insult. So to sort of summarize the findings is, clearly the chemistry says that certain of the source waters and groundwaters are controlled by natural phenomena. Wastewater chemistry is strongly controlled by anthropogenic chemicals. The thing on the islands here, though, is almost all of that wastewater is disposed of into the void, the unknown. It's put down an injection well, it's put into a lava hole, or it's put out in the ocean through an ocean outfall. So fortunately for the islands, you don't see very much of an effect of wastewater impact on the surface water or groundwater systems. That could change in the future as the climate continues to dry and the population grows up. So, or as more water reclamation and reuse begins to be applied inland. We might anticipate this could change. Also keep in mind, I've only focused today on what's dissolved in the water, and we tried to focus on water systems that are the average. We didn't really, with the exception of a few wastewater treatment plants, these are streams. They're not like targeted hotspots. But the take-home message really is, it's very important to take this holistic approach when we're trying to assess water quality, that if you're out there measuring quantity and abundance, you should also be measuring quality and what's in that. Because when we think a lot now about water availability, that's a big topic on the mainland. It's probably an important issue out here. I like to say you need to be thinking of water availability and suitability. Not all water is suitable for all purposes. And that kind of is shown in this final slide, which is one of the unique characteristics of what we call the Anthropocene now, is that humans are dominating the planet, and that includes the global water cycle. Now here's a statement from the USGS. This is our typical water cycle diagram. It's used throughout the world, but if you kind of look at it, you go, wow, there's a lot of parts, but there's nothing to do with humans. It's all about natural. Oceans evaporate, clouds condense, the precipitation runs. But a study that was done by Abbott et al. Here, just came out in Nature Geoscience this year, did some studies, and they have found that human appropriation of freshwater systems equals or exceeds 1/2 of the global river discharge. So if you take all the rivers in the world and their discharge, that's about how much, about half of that volume has been appropriated and used by humans. And this is important because it lets us look at like green water. Humans use green water to irrigate pastures and grow crops. We use blue water to bathe, to drink, to run our industrial processes. But once we take and use this green and blue water, it becomes this gray water, which is this fresh natural water, that rainfall, that when it comes back into the ocean, it's not the rainfall that just fell on the ground. It's the rainfall that fell on the ground, got into the aquifer, pumped up, used by a city, discharged as a wastewater treatment plant effluent, with all of the associated chemistry and biology in place in that. So to be able to get a better understanding of processes like this, we really do have to continue this integrative science. I'm not sure the disciplines that are represented here, but I would encourage everyone to reach out, try to interact with scientists that can contribute what you think is important, but you aren't able to do it yourself. And that will help us as we start going after sustainability. So with that, I'd like to conclude, and I'd be happy to take any questions, comments,